So I want to talk about heating and cooling curves because with heating and cooling curves, the common misconception is where things are taking place and things like that. So for the first part, we want to look at temperatures. So let's say these are both heating and cooling curves for water. Okay, what that means is that water has two pretty important temperatures, where you have 0 degrees Celsius, which is where where it melts or freezes, and then also 100 degrees Celsius, which is where water boils or starts to condense, depending on whether or not it's heating up or cooling down. So when water's heating up and it's below 0, it is a solid. Now remember, a solid is going to have molecules really close together, and they're going to have strong intermolecular forces. Okay? Now, as the solid begins to heat up, right, the temperature, let's say this is negative 20 degrees Celsius, as it starts to increase its temperature, the molecules are going to speed up. So anywhere that there is this slanted line and a temperature change, that means the molecules are speeding up. So that means it happens there and here and here. Now, what happens though is when the solid water, ice, reaches 0 degrees, it will begin to melt. And so when it begins to melt, it will turn into a liquid, and that liquid will start to heat up. And once that liquid has reached 100 degrees, vaporization will start to occur. And then when everything is all vaporized, it's a gas, and that gas will begin to heat up. Now, an important thing to note is that your vaporization and melting, your phase changes, these happen on the flat sections of a heating curve. And this is because the temperature doesn't change. So during a phase change, the temperature does not change. Okay? And so that means, well, the reason why is because energy, instead of being used to speed up the molecules, which would cause a temperature change, the energy is being used to break the forces. That's what the heat is being used for. Heat can do one of two things. It can either break or form the forces, or it can be used to speed up or slow down the molecules. Okay, so in a heating curve, molecules are going to either start to speed up, or during the phase changes, they're going to break the forces, because the gas molecules, they are spread all over the place and have no forces connecting them. Okay, and liquids, they're spread out but still kind of close. We've drawn pictures of them before, and they have weak forces. So as you're heating up, your forces are getting weaker and weaker until they're completely broken. And so that means that the energy has to be used to break those forces. Now, a cooling curve, it's exactly the opposite. A cooling curve starts where the water is a gas at this high temperature. And then when it cools down to 100 degrees, it will undergo condensation. And when it undergoes condensation, it turns into a liquid. And when it turns into a liquid that eventually cools down enough to get to 0 degrees, it will start to freeze. And when it freezes, it becomes a solid that can continue to get colder and colder. And so again, same thing. On these angled parts where the temperature of the gas, the liquid, or solid is changing, you know that the molecules are going to be slowing down. And the reason why you know they're slowing down is because the temperature is getting lower. If the temperature is going down, the molecules are slowing down. If the temperature is going up, the molecules are speeding up. Whereas here at condensation and freezing, this is when you are forming or you're making the new forces, because you're going from the gases, which are spread very far apart, to the solid, which is very close together. And so with that being said, when you're looking at a heating curve or cooling curve, during a phase change, if you need to do a calculation, you should, for example, if you want to measure the Q needed, so the amount of heat or energy needed to actually melt a certain amount of something, you would use your Q equals M times delta H of either vaporization or Q equals M times delta H of fusion. Okay, now remember, vaporization is used for condensation or vaporization, right? Either one. But fusion is used for melting or freezing. And so you need to know which one to use when. And the difference between condensation or vaporization is when you look at a cooling curve, in order for the temperature to be going down, this has to be an exothermic process, which means your Q should be negative, and that means that your delta H of either vaporization or fusion should also have a negative sign in front of it. For a heating curve, it's the opposite. You're heating up, so it's endothermic, which means Q should be positive, and your delta H should also have be positive. So that's one thing to keep in mind. Now, if you're having a temperature change, so all of the angled lines, so solid, liquid, or gas only, that is when you're going to use Q equals M times C times delta T. So Q equals MCAT for your formula. So depending on what they're asking you to do. So hopefully that was helpful.